Okay, so here's just a summary of what we've been through. We said that we can treat events as either coalescences or mutations. Then our total rate is the sum of the rate, and our average waiting time is like this. And then we said, what's the probability that our ith event is our first coalescent event? And we wrote down that it looks like this. This is slightly different than we did it in the last video. It'd be worthwhile convincing yourself that they all jive. And that means our expected number of events until our first coalescent is equal to this, which means that the expected number of mutations that occur before our first coalescence is just this minus 1. And so we get this simple expression. The number of mutations that we expect before the coalescent is just m over c. Okay, so now that means that in our sample, what we're doing, this is giving us our expected number of mutations that occur in this interval, in our first interval, in our second interval, in our third interval, and so forth. Right? And so let's work through this for this one, for the next one, for the third, and we're going to see that this changes for different intervals. Okay, so now we're going to basically take this m and c, set it equal to something, and then do the ratios. Okay, so what's our coalescence rate of coalescence? Well, we said it's 1 over n times our number of pairs of lineages. So n divided by, n choose 2. We said that n choose 2 is equal to n times n minus 1 divided by 2. And so we get this whole expression. Well, what's our mutational rate? Well, let's just call the mutation rate for our whole locus u. Okay? So that would mean for the whole sequence that we're studying, we're not studying an infinite sequence, we're not studying a hypothetical sequence, we'll be studying a single sequence of length 724 nucleotides or whatever. So let's imagine that the rate of mutation across that whole gene is equal to u for each sequence. Okay, so then the mutation is basically just u times the number of independent lineages that we're studying. So in this first interval, where we have n different lineages, we have n different branches, each mutating at this rate. And so our rate of mutation is equal to n times u. Okay, so then let's fill this in. Then our overall rate is equal to nu plus n minus 1 divided by 2n. And then our 1 over RT, that's straightforward. So then let's get down to here. So then this would be, so here we're going to get into the ratios. So let's actually break this out and see what our m divided by c plus m and what our c divided by c plus m are. Okay, so m divided by c plus m is going to be equal to nu divided by nu plus n times n minus 1 divided by 2n, which we can simplify. So we can just get rid of these n's, and we get u divided by u plus n minus 1 over 2n. So not the world's simplest expression, but still fairly straightforward. To me, somewhat surprising that we can write down something so simple. And so then we expect, so our expectation then is m divided by c. So the expected number of mutations that we have in this region is m divided by c, which is nu divided by n times n minus 1 over 2n. And if we simplify that, we get 2n u divided by n minus 1. Okay, so the number of mutations that we expect in this interval occurring across all 5 sequences is equal to this. So then let's see how that changes. So if we start with a sample of 5, then we would expect our number of mutations here to be 2n u divided by 5 minus 1 by 4, and here we'd expect 2n u divided by 3, and here we'd expect 2n u divided by 2, and then we'd expect 2n u divided by 1. So notice this goes up. We expect 4 times as many mutations in this last interval as we expect in this first interval.